So next up, diving straight back into our agenda, prepare to have your perspective shifted as Scott Evans, Principal Scientist of AI Machine Learning at GE Vernova, explore the potential of causal AI in tackling the climate crisis. Remember to keep your questions coming in Slido.
Thanks so much. So I have a joke. A photon was checking into a hotel. Yes, a photon, bundle of light, was checking into a hotel. And the concierge asked, "Can I help you with your bags?" And the photon said, "I don't have any bags. I'm traveling light." So this is a little bit kind of related to that. So I'm with GE Vernova. GE has separated into 3 different companies, and I've spun out with the Vernova energy-related businesses. We've actually been working with causaLens as part of a healthcare project. I won't be talking about that today, but that's another one, medically related, working on decisioning and causal inference. But what I want to talk about today is causality in green AI. And the big idea that I just like to convey is that energy is not just this thing that we do to kind of put a big power plant up next to the data center so everybody can do their AI. Energy and AI are intrinsically related. It goes back to entropy and thermodynamics and entropy and Shannon. Learning and randomness and entropy are deeply correlated. And so the challenge, I think, in order to really harness AI for solving the climate crisis is to optimize the what, where, when, and how we do our causal AI. We do any of our AI so that we can minimize carbon, maximize learning, and even stabilize the grid. So as Judea would have us, we'll start with the why. So why is energy's going, the temperature's going up, right? The climate is continuing to be a crisis, and it's no longer the case that compute and it is a small part of that. So this is a graph that just kind of shows the trend in how much energy is used for compute. By some estimates, by 2030, 30% of energy could be used for compute in some ways. This is just out last week or last month from Goldman Sachs, showing a 4-fold increase in data center power, terawatt hours rather, from AI going up. So, in 1973, I think Nixon signed legislation to limit the speed limit to 55 miles an hour, right? It wasn't safety related. It was related to the oil embargo. It was related to an energy crisis and the fact that, the wind resistance of a car goes up by, the energy consumed goes up by the cube of your speed, right? So if you limit your speed, you limit the energy. We don't really have constraints, right? Nobody's going to give me a ticket for coding badly. If I do a brute force search instead of distributing my models, I could put my models in a green AI place, or like powered by wind turbines, or I could have it powered by coal, right? And people are looking at this, but I don't think we're really capturing the total opportunity. So how can we optimize the what, where, when, and how? Well, the what part is huge. So this is a power curve for a wind turbine. So I've worked in optimizing wind turbines for about a decade now, and it all comes down to this power curve. When we sell a wind turbine, we actually sell a power curve that says how much energy you're going to get for a given wind speed. And that wind speed is generally measured by an anemometer that sits behind the blades of the turbine, and it tells you, at 8 meters per second, you're supposed to get a kilowatt. At 9 meters per second, you're supposed to get, 1.2. And so part of our challenge has been to optimize this power curve by, pushing it up and to the left. Anything you can do to make your energy more efficient from your wind turbine, it's just gravy, right? Because the fuel is free. But there's challenges in figuring that out. So how can I even use software and things like that? There's hidden variables, right? The only thing that matters to a wind turbine is not just the wind speed, at this one sensor after it's already gone through the blades, right? There's other atmospheric factors in effect. How do you do interventions? How do you do randomized trials? How do you do natural experiments and balance the data? And then furthermore, how do you validate the gains? One of the places where this became apparent was we had a wind farm in Texas that was getting 10% less power by the power curve at night. And we're like, oh my gosh, the turbine's afraid of the dark. But obviously it wasn't that. It was another factor, a hidden variable that we didn't have on our causal graph, or at least we hadn't put it in there. We kind of knew about it. But so there's this other factor, shear, which is the vertical gradient of wind speed with respect to height, right? And it just turned out in this town in Texas, the way the weather happened when the sun went down, the atmosphere would stratify, and you'd have a profile that went from like this in the day to this at night, which, again, the cube of the energy relates to, the cube of the wind speed relates to the energy. So whatever we were measuring on our sensor behind the nacelle was not really reflecting the total energy going through the blades. But it also brings up the fact that you can operate your turbine differently under these conditions than under these conditions. So how do you figure out a causal model so that you can optimize that? And as Judea has taught us all, the probability of y given x does not necessarily equal the probability of y given that I do x, right? If I notice that the data show that high wind shear relates to high turbine pitch and higher power, that doesn't mean necessarily that if I pitch the turbine blades into the wind, I'm going to get more power. I have to figure that out in a causal way. So we would do basically a randomized trial. We do basically A/B testing and run our turbines through different settings, different options, and notice when does it get more power, and put that into a surrogate model. And now, because it was trained on a randomized trial, that's essentially a causal model. Now we can prescribe these operational parameters for the turbine and get an extra % of energy essentially for free through Causal AI. Another way we try to get energy through basically AI. In this case, the AI was basically simulators, right? And I would argue, we've been doing Causal AI for the longest time when we do simulations of physics, right? I mean, the physics is inherently causal. It's when we want to cast the data back into a model and assume that that's the same that we kind of get in trouble. But our aero engineers figured out that these vortex generators could be put on the blades, and they basically concentrate flow to keep attached flow longer on the blade so it doesn't stall, right? So we put these things on the turbine thinking, hey, this is great. This is an easy way to get another 1% power. The only problem, that pesky power curve showed up again, and it actually showed that we lost power based on the that upgrade. And we're thinking, no, that's not true. So they went through like an experiment. They said, okay, we can do this wool tough test, right? So they actually kind of tape these little strands of wool to the blade in a grid-like pattern and then film it from the bottom. And when the turbine blade is going, if the wool deflects perpendicular to the motion, then you have attached flow. You're not in stall, right? Whereas if it's just kind of floating around, then you're stalling, right? So this verified that with the vortex generators, we had a region of attached flow reduced by about half. So we're like, this is great. It is working, but the customer's still like, wait a second, I don't understand. So we developed more AI models to basically prove this out, and not unlike the last talk where we kind of created a synthetic model to show what is the expectation of power for our turbine based on other sensors, not the one that was confounded by the upgrade that we put on, right? So we created an AI model for the expectation of every individual turbine in the farm based on the power of every other turbine and the and the angle of the wind and all that kind of stuff. And in that way, we were able to kind of show that we had in fact produced more power. So there's all sorts of opportunities for causal AI to provide green energy. Another area we're working is in nuclear. So I was at the ARPA-E summit a couple weeks ago, just last week actually, and we have 2 programs in nuclear that are using essentially causal AI to harness green energy from nuclear power. One is in trying to figure out how to reduce the maintenance costs. So this one program was basically, a lot of labor is spent in nuclear power. A lot of times we're chasing false alarms in, PHM kind of problems. And so figuring out how to, optimize that, we came up with an inverse model for optimal sensor placement. And so basically, it lets you decide, where should I put sensors in my plant, extra sensors, so that I don't have as many false alarms, so that I can trade the cost of adding the sensor for the value of, detecting something early if it goes wrong, not missing something that I should have caught, or not having a false alarm for something that wasn't really real, right? So a lot of times we design these plants with, the sensors that are prescribed based on what always happened, but being able to answer that counterfactual of what would be the total lifetime cost be if I put an extra sensor here, or if I put a higher quality sensor here, or if I put two lesser quality sensors in different places. And so those are the kind of inverse models we're working on. Another project we're working is to try to capture some of the energy that's just sitting around in all of the nuclear power plants. There's 90% of the energy remains in used nuclear fuel. It's you have so much uranium that starts in there, and then you use about maybe 10% of it, and then you trade it out. At the Upper East Summit, I kind of try to make that point. I had a big vat of M&Ms. 90% of them, these white M&Ms, carbon free, and the other ones not. Just to kind of illustrate the point, that's just sitting there. But some of the blocks to that are things that Causal AI can help us do. For one thing, we can figure out where to put sensors in reprocessing plants so that we can, track the material carefully. So there's a whole, backlog of opportunities for using green AI. But I think one of the missed opportunities is the fact that we're not optimizing what AI we do with where, when, and how we do it. And so here's just a simple example. This is my daughter Abby and her bunny Nikki. So Nikki the bunny in upstate New York we'd put her in the garage in the winter so she didn't freeze. And even then, I begrudgingly bought a 1,500 watt heater and plugged it in an electric heater. Uninsulated garage. It really, tore my conscience, but the bunny stayed alive, thankfully. But then I got the idea, and some of my buddies at the G Research Center helped me go on eBay, and I bought an ant miner. I bought a Bitcoin crypto miner, 1,500 watts. Put it in there. It was a little loud. I don't think the bunny liked it that much. But saved 1,500 watts residual heat from that thing, kept the bunny alive, paid for a semester of college for Abby. So started to think, okay, what if instead of a Bitcoin miner we had, some kind of a HPC or workstation that, Tom could put, some of his federated learning of, PC versus FCI or different types of causal discovery algorithms there. What if we did computational fluid dynamics? What if we had this distributed so that, my neighbor also had it, and we can kind of turn them on and off to stabilize the grid, or turn them on and off to, set the temperature. If we can optimize all those things together, we have a great opportunity to do good. So we've been working, my colleague Tapan and I and some others from G Research have been working on this whole kind of concept of optimizing those things together. And so imagine a world where you have an HPC at every power source, right? Acting as kind of like a shock absorber for the grid. And like that traveling like photon, you can move your AI job to where the green energy is. And you can, if Texas freezes, as it did, you can move the power to Maine, or you can kind of take that load and use it. It's very, very movable, right? Through fiber, you can move bits a lot easier. Others have done a lot of great work in this area. So we want to basically move the AI loads to where the green energy is, schedule the AI loads to stabilize the grid. But it's more than just like a load management thing. Like people have done energy management for a long time. It's like, you sign up and they'll turn off your pool at an hour and it's okay. And you can get a little bit of that, through a number of different mechanisms. But AI and energy are so related, right? So I come from like an information theory background. This is kind of a curve. You'd call this, the Kolmogorov structure function, but it kind of shows how you can see in this blue curve the performance of an AI algorithm as a function of the complexity, right? You add more complexity, and at some point you hit, an optimal, and I think we all know that at some point you overfit, right? So this K star here is kind of like the optimal complexity of your algorithm that balances the variance and bias trade, essentially. And so today, what we do is we tend to just overfit everything, right? The deep learning models just try everything and then prune it back, right? So we're going all the way over here, spending this much energy, and then pruning back to the same performance that we could have gotten perhaps by just adding a little bit of complexity at a time. So we've kind of coined this term additive AI. It draws from additive manufacturing. Additive manufacturing is in contrast to subtractive manufacturing, manufacturing where you maybe punch a part out of a piece of sheet metal, right? And there's a lot of waste. As opposed to additive manufacturing, you add a little bit of material, a small amount at a time, and you don't have waste. And it's a little bit maybe more intentional, but it saves on the waste. So we're kind of putting out that paradigm, but also since AI and energy are so linked, one of the results we have, my colleague Hao and Tapan and I and others have, we have this paper out where we actually found that if you do this kind of thing, you might even get better performance by starting with low complexity and moving up. So this is a paper we had at the AAA AI conference. So all these things kind of work together, and we've kind of developed this kind of framework that I call the entropy economy, right? And it's really kind of drawing on that idea of jointly optimizing the learning, which is really kind of compressing the data. If you kind of think of your training data as this uncompressed gas and you impart energy on it to compress it into this small machine learning model that you can fire and get a prediction back. You have like a whole kind of Carnot engine kind of cycle in learning. And we would get excited if we got 1% more efficiency out of a gas turbine or 1% more out of a wind turbine. How much more can we do by moving our AI in concert so that we can make sure that we're not burning up non-green energy when we could, right? AI can pause for a moment, right? A lot of times we do our jobs and do we need it instantly? Maybe not, right? So that's the kind of framework that I think would be great. So in closing, I'd just like to ask, think of your AI jobs as one of these M&Ms, right? And to kind of riff from Benjamin Franklin, a ton of carbon saved is a ton of carbon earned, right? If we can kind of prevent, carbon credits are great, it kind of drives some good behaviors, but basically, essentially, is giving us a right to pollute later. If we can optimize the what, where, when, and how of our AI, we can prevent the need to pollute at all. And so please just ask that counterfactual as, if I had done this AI differently, if I had done it in a different place or, with different kind of quality of service constraints, could I save carbon? Because causal AI is essential to combating the climate crisis, but it's also a great opportunity, I think, to really harness these things together. Any question?
Thank you, Scott. There were a few questions. We've got a little bit of time. You did well, thank you. First one, for the randomized control trials, what's the unit of randomization? So is it turbines, or for the same set of turbines, you try different configurations per time unit?
So we would typically, sometimes we have a control set of turbines, sometimes we have just, we found that it's really efficient to just have the turbines randomly, turning from, like 20-minute intervals for certain things. Wake optimization is another real big challenge. And in that case, we don't have really, it's really kind of optimizing a natural experiment. But we can kind of take advantage of the fact that these turbines aren't like Porsches where they turn on a dime. There's like some slack, right? So you can kind of see, what is the effect on the overall farm when a turbine is 10 degrees, steered a certain way, that kind of thing. But it tends to be, usually A/B testing in some kind of a randomized way with some kind of a finite minimum of duration of toggle.
Brilliant, thank you.
Yeah.
And one last one. It is common to use reinforcement learning to optimize processes. How does causal AI compare to reinforcement learning? advantages, disadvantages? In 30 seconds, obviously.
30 seconds. I'm not an expert on that, but I think it's a great way to kind of bring in the physics-informed machine learning with the data-driven stuff. So I think it's very complementary in my view.